This week on Today in Space.
We only gone as deep as 6 miles into the surface of the planet or towards the core.
I think I can't remember if it's 6 or 8 miles, but it's in that order of magnitude. Yes.
What's the, I guess, I know part of this answer, but what is stopping us from going any deeper?
So basically, every time you get deeper and deeper in the Earth, the pressure increases and the temperature increases. And if you've ever been scuba diving or tried to dive deep, you have a sense of how pressure can affect the human body. And the same thing is true for equipment. The key thing to remember here is scientists are humans.
Yes.
And humans very much have their own kind of biases and beliefs and so forth. And so you have to kind of always try and keep yourself grounded and understand that, your ego is not embedded in that thing you discovered or that theory you have, right? The important thing about being a scientist is to be able to change and to follow the reasoning and the data.
Welcome, everybody, to another episode of Today in Space. I am your space science podcast host from the East Coast, Alex Girofanos. And today we're back for another episode of People of Science. And we're very excited today to talk to Dr. Sabine Stanley, the author of What's Hidden Inside Planets, coming out of Johns Hopkins Press. Dr. Sabine Stanley, thank you for joining us.
So happy to be here.
Awesome. So it's great to have you. I've loved the book so far. And what I'd love to do before we get into that, give us a little bit about your STEM origin story. Where did this all start? Where did it begin? And what were some moments that made you think, oh, this is what I want to do?
Yeah, great question. So there's first of all a real origin story here in that I grew up in an impact crater, which is basically a giant hole in the ground where a meteor about 1.8 billion years ago smashed into the surface of the Earth and created a big hole. That brought up a lot of resources, natural resources from the deeper interior. And so it was a mining town. So I actually grew up in a place that was really related to planetary science. I didn't really know much about this while growing up, but I think it must have been somewhere in my subconscious.
Yeah.
But really where I got interested in this, I was a kid who kind of liked science and math, but didn't really know what to do about that. I didn't have any family who were in academia or professors or scientists. So everyone thought I was going to be a doctor. Then I took my first biology class that involved a dissection and realized that, no, that was never going to happen for me. I was really fortunate in my undergrad days to have an incredible mentor at my university. And he taught me my first year physics class. But he was a geophysicist. So he was someone who studied the physics of the Earth. And so he kept going back to examples that involved Earth and the planets. And it was all very interesting. I was like, So eventually by about my third year in my undergrad degree, I realized, you know what, I think I want to study planets. And that was how it all went from there.
That's crazy. That's crazy. Now, when did you find out that you grew up in an impact crater? Was that like something that the town was aware of, or did you learn that?
Yeah. So it was just my cluelessness, not the town's, right? Everyone there
absolutely.
knew. But you also, you hear it as a kid and you don't understand the importance of that or what it really means, right? You're like, okay, yeah, it's an impact crater. There's lots of mining going around, but you don't realize the sort of planetary implications of it.
Yeah, I have a somewhat similar story. So I went to school for aerospace engineering. I live right by a local airport, and I was seeing planes all the time. My favorite thing with my grandfather was the gliders. It was always there, but like you, and I talk about it throughout the podcast here. Sometimes it just doesn't click until it clicks.
Yeah.
So tell me a little bit about the mentorship too, and maybe some other people you had in your life that you think were kind of instrumental, because a lot of what we're interested right now in the podcast is like that human factor. And I think that's one of the things that I love about your book is that it's not coming at it from a super technical, although there's plenty of technical knowledge in here. It's coming from a human perspective. And I like that you intertwine parts of your life in there. What kind of people have helped played a role to get you, where you are today?
Yeah, great. So I think the first person was actually my high school music teacher. His name was Dick Van Ratshoven. And he was, although I'm not in music, it was something that was really a part of me and still is. And he was a person who really inspired in me a love of teaching and a love of kind of engaging with people for whatever they're interested in and so forth. And he was just a really amazing human being. Then, while also in high school, I have to say that sort of after class, I'd get home and get ready to do my homework, and you sit in front of the TV in those days. And, you know, we didn't have Netflix at those times, so you had to watch whatever was on. And at that time, Star Trek: The Next Generation was on, and I started watching it. Oh, there you go. Yeah.
Oh, yeah. Oh, yeah.
And I mean, so I tend to consider Jean-Luc Picard, Captain Jean-Luc Picard, as my other mentor, because I really saw him as someone that I really wanted to either interact with or wanted to develop some of the same characteristics as, maybe the way to think about it.
Absolutely.
So that was a huge influence and really kind of led me into more the space route than, let's say, some other science. I realized that this idea of discovering other worlds out there and what they're made of and what can happen there was really exciting. And then the third mentor was my university professor. His name's Jerry Mitrovica, and he was just a really human person, right? He was an amazing scientist and an amazing lecturer, but he would always regale us with these stories, and they just kind of brought him down to earth, right? It was like, oh, yes, this is a fancy, famous professor, but he does silly things just like we do, right? And it just really seemed like, you know what? Maybe I could do this. And that really helped. And he's now a dear friend, and we've collaborated and we're on papers together and everything.
Now
so
that's really cool. So tell us a little bit about the college experience before we dive into like planetary science and the insides of planets. PhD. You went for that. How was that? Because I've talked to a few folks who were in the middle of it, have done it. Like, it always seems like it's slightly different for everybody.
Yeah, for me personally, so I was the first in my family to kind of go to the PhD route, and I didn't really know what to expect, right? I think I kept going. I decided to go and do a PhD because I liked school, wasn't really ready to leave it to get a real job per se, right? And so I was like, okay, the next degree I can get is a PhD. And I moved to the US. I was in Cambridge, Massachusetts at Harvard University. And that was it was a great time because I was surrounded by some amazing colleagues and friends, and we kind of all learned together, and that was really great. But I also I suffered from the imposter syndrome and not knowing anything about it. Especially, I was doing my PhD in geophysics, and my undergrad degree was in physics and astronomy, and I had never taken an earth science course whatsoever. So I remember going to my first geophysics classes, and they kind of were right in, and I had to kind of raise my hand and go like, what's a subduction zone? Because I had no idea. These are things that you might learn in like your intro to geology class, right? And I just had no idea. So it was a bit of a learning curve, but that was actually kind of the norm in earth and planetary science departments. These departments where we study planets and we study the earth, everyone comes in with very different expertise. Some people come in as like experimental chemists, other people might come in as mathematical modelers and so forth. And we all just kind of get there and we realize we like using our techniques all to study the earth and planet. So we all kind of learn from each other. And I really appreciated the ability to learn and to teach others about what I knew going in.
Yeah. And teaching, I think that's one of the most valuable, like fifth gears that you can do when you're learning something is once you get to a point where you can start teaching somebody else, especially like in another class, that's where it really starts to stick.
Absolutely. 100% agree.
So break it down for us. Where did your journey towards the inside of planets come to? So as a planetary science, I feel like there's kind of a wide breadth of different places you can go, and you went right to the center. Tell us about that.
I didn't think of it that way. That's a great way to think about it. I don't know if this is going to be a satisfying answer, but it was basically by accident.
Love it.
So it was my third year undergrad, and I had been planning to become like a cosmologist or do something, study black holes or something like that. And by that point, you're actually learning about those things in your undergrad classes. Right. And I was like, you know what? All that stuff's kind of really far away. And I don't know if I'll ever like be able to touch it or be able to kind of study it up close. And so I realized, you know, I want to kind of do something closer to home, more planets like. So I went to my mentor, Jerry Mitrovica, and I said, hey, I'd like to kind of for the summer go somewhere and do a research project as an undergrad. And he said, you know what, I have 2 colleagues at Harvard who are doing some work. Maybe you'd like to work with one of them. And I was like, okay. So I got these 2 professors at Harvard to send me ideas for projects. One of them had to do with studying tsunamis produced by earthquakes. And another one had to do with the magnetic fields of Uranus and Neptune. And I knew nothing about any of these topics. And I just kind of went, Uranus and Neptune, magnetic fields sound cool. So I picked that one. And so my intro to this was really just kind of what was available at the time. But it really brought together what I realized when I was studying it is I really enjoy sort of the modeling aspect, the computer modeling, doing these cool simulations of fluid flows and magnetic fields.
Yeah.
And so I could get that out of studying these magnetic fields of planets. So and the rest is history, basically.
That's crazy. No, I love that answer. I actually think that's what I was looking for, because I think most folks, when they're looking to get into this career, I did this myself. You kind of look for the job that you're going to do, and it's almost never that, or most people don't ever do that.
Yeah.
So you followed what was interesting to you, which I think is kind of the best advice we could give to folks who are looking for that. So tell us a little bit about, especially for folks who may not be aware about planetary science, give us a little breakdown of what it is that you're doing, and then kind of let's jump into the book and talk about what it is.
Sure. So what I do, I'm really interested in what happens in the deepest parts of planets, both Earth and all the other planets as well. Because in the cores of planets, you actually generate magnetic fields. And the magnetic field, although it's generated deep inside a planet, is able to escape the planet and surrounds us. For example, here on Earth, we have a magnetic field that surrounds us. And this magnetic field is incredibly important for it to be a nice place here on the surface of the Earth. So for example, the magnetic field shields us from cosmic rays and high energy solar wind particles that would bombard the surface if it wasn't here. And that makes the place kind of less radioactive, essentially. You experience less high energy radiation is what I should say. And also it is because it's not being bombarded by all these solar wind particles, we get to keep our atmosphere, which is kind of cool because we like to breathe, right? So these are all the sorts of things. So I like the fact that when you're studying the deep interior of the planet, first of all, it's really hard to study. Like you can't just go drill down there and check it out, right? So you have to come up with sneaky ways to try and investigate the interior. And I kind of like that. I like using this sort of detective approach where you like, what sort of evidence could tell me about this region that I absolutely can never visit or see?
Yeah. It's very Sherlock Holmes. I love that.
Yes.
So is this true? I think I was seeing this the other day. Have we only gone as deep as 6 miles into the surface of the planet, or towards the core?
Yeah, that is correct. I think I can't remember if it's 6 or 8 miles, but it's in that order of magnitude. Yes.
What's the, I guess I know part of this answer, but what is stopping us from going any deeper?
Yeah, great question. So basically, every time you get deeper and deeper in the Earth, the pressure increases and the temperature increases. And if you've ever been scuba diving or tried to dive deep, you have a sense of how pressure can affect the human body. And the same thing is true for equipment. So as the pressure gets higher and the temperature gets higher, equipment just does not like existing in that environment. So the deepest we've ever been able to go in a borehole with drilling equipment is, in less than 10 miles. And
Crazy.
Like the deepest human mines are less than 2 miles, right? So
yeah, that's wild. Especially when you put it to scale of just how big. I mean, our planet's not a big planet, but there's still a lot more.
Yeah, so if you think of from the surface of the Earth to the center, right, you're talking about thousands of miles. So we barely scratched the surface.
It's crazy. That's crazy. So tell me a little bit more about how we use these kind of techniques to estimate like different planets that are out there and what's at their cores.
So I like to tell people that it's kind of similar to what your doctor might do. Like, let's say you show up at your doctor's office and you're like, I have an ache or something. Right. The first instinct of your doctor, hopefully, is not to kind of like cut you open and look for it, but is instead to run a bunch of tests. And so the types of tests you can do, things like CT scans, MRIs, those kinds of things, are basically ways to use light or force fields to image the inside of you. And we do similar sorts of things for planets. So we can use a range of different fields. So we use gravity, for example, we use magnetic fields. And we also use waves from quakes caused by earthquakes, for example, here on Earth, or Mars quakes on Mars.
Yeah.
So we can use these types of sounding and imaging to really see what is going on deep inside a planet.
And there was a part of your book where you mentioned how you were comparing kind of this technique of looking at other planets and kind of classifying them as families, or DNA of a different planet. Could you go more into that? I loved that comparison.
Yeah, thanks. So believe it or not, all the planets in our solar system, we all kind of came from the same stuff, right? There was initially this gas and dust filled disk that surrounded the growing sun at the center. And all of that material, like, it all kind of came from the same place. So it's not surprising that all the planets in our solar system, they have some similarities, just like people in a family will have some genetic similarities, right? But they're not all the same, because they all kind of sample different parts of the genetics spectrum, right? So in planets, they sample different parts of the disk that surrounded it. They also experience different environments, right? So there's a nurture part of that. That was the nature part. There's also a nurture part. The planets closer to the sun, we're in very much hotter temperatures than the planets further out in the solar system. And so you can actually now, when we look at the planets, get a sense of how those types of conditions affect the formation of a planet, right? Earth would not be Earth if we were sitting out where Jupiter sits, for example. So that's one way to think about it.
No, that's so good. It really makes me think about how much is really out there. I think for a long time we were kind of stuck in this mentality of Carl Sagan's birthday was recently, and thinking about, there was only one exoplanet discovered when he passed. Think about how many we have now. Just to think about what he would think about that and he would say about that, and how much he was so good at explaining how massive things are, and how special we can be. What is kind of in the last 5-10 years, even for you, what's changed in your perception as a planetary scientist as to what's out there?
Yeah, great question. So sort of, it's going to sound contradictory, but two things. First of all, there is so much out there, right? We've currently discovered over 5,000 exoplanets, planets orbiting other stars. And, we're only limited essentially at this point by the amount of time we've been observing things and the technology. So things are we're going to just keep discovering more and more and more. Then you get a spacecraft like JWST, the telescope that was launched last year. Oh, look, there it is right there. Here. And it's going to completely change just the quality of information we can get. So with JWST, we'll be able to analyze what the atmospheres of these planets are made of. And if you get to know what the atmospheres are made of, you can kind of start making some inferences about what's going on the planet, right? Does it have life, for example? I think that's a question. If someone from space, if aliens out there in space looked at the Earth and studied our atmosphere, they would be able to tell that life existed here. And so we're basically asking the same question out there. Now, although I say all of that, and I say there's so much out there, so many possibilities, I really do think that Earth is quite unique. And we need to really appreciate the fact that a lot of things had to go right in order for there to be life here. And sure, there's probably life somewhere on another planet, but it's not that easy to just go to another planet and make it a nice livable planet, right? There's these ideas of going to Mars or other places and we'll just kind of recreate Earth. That's not going to happen, right? We need to kind of work on understanding our planet and making sure that we keep it a nice habitable place to live. Sure.
And give me an example, if you would, of just one way that Earth is special and as unique as you were saying.
So Earth is the only planet in our solar system that has liquid water flowing on the surface regularly. And that's just because we have the right conditions in terms of the radiation getting from our sun and sort of the atmospheric pressure on the surface, right? So you need to be a certain distance away from your star and getting the certain amount of radiation, but you also need to have kind of the right size of planet to have kind of a rocky composition. And then you need to have the right sort of stuff in your atmosphere. And admittedly, we know we have one data point in terms of what conditions do you need to make life, right?
Right.
So
Right.
who knows if there are others, but based on what we
Yeah.
know, right? If we look around there aren't that many places in the solar system that have those conditions.
So what about places like Enceladus? Are you excited to be able to get hands-on with something like that?
So you're right. So there are a few places that we know have global liquid water oceans. They're all below the surface though. So there's none flowing on the surface where we can easily go and check them out, right? So the moons in the outer solar system has a ton of water. It's just really cold out there. So it's all like frozen, right? So Enceladus, Europa is another one that's a moon of Jupiter. They have this nice ice shell, but underneath that, maybe we don't exactly know how deep, but you're talking tens of kilometers deep, there is a liquid water ocean in those bodies. And so there might be life in there, and we just have to figure out how would we detect it? How could we sample it? But the Europa Clipper mission, scheduled to go to Europa next year, is a good place. The moon that's actually most exciting to me is a different moon. It's the moon Titan of Saturn.
Okay.
So now I'm going to try to convince you that Titan is the place to go look for life.
I'm listening.
So first of all, Titan's just really cool because it's the only other planetary body in our solar system that has a nitrogen-based atmosphere like Earth and has a thick atmosphere. So the pressure at the surface of Titan is about 1.5 atmospheres.
Okay.
Now, Titan's small, so its gravity is low. Okay. So the coolest thing about Titan is if you, for example, strap a couple pieces of cardboard to your arms and flap them while on the surface of Titan, you can fly. So buoyancy is really easy on Titan. And the Dragonfly mission, which is scheduled to go out and visit Titan, is essentially going to do this. It's basically a dual quadcopter that's going to fly around, land on the surface, do a bunch of science, get back up, fly somewhere else, land somewhere else. So the amazing thing about Titan is it's the only other planetary body in the solar system that also has liquids flowing on the surface. Now, they're not liquid water, they're liquid hydrocarbons, things like methane and ethane, so no swim in there or anything. But you're basically talking about the building blocks of complex molecules, right? The things that we think eventually make amino acids, proteins, life, right? So you have almost all the right conditions and ingredients for complex chemistry and maybe even life on Titan right at the surface. So I think it would be really interesting, and I'm excited to see what the Dragonfly mission finds there.
That would be very exciting, especially with we have Ingenuity on Mars with way less atmosphere, flying around like a kid with caffeine. I mean, so this is Titan's going to be a playground for Dragonfly.
Absolutely, absolutely.
All right. I like it. That Titan's definitely higher on the list after that. Being able to fly is pretty sweet. So I think if all you need is cardboard, I think I'm down.
Yeah.
So let's talk about some of the recent missions that have been happening, like Psyche, that's launching to 16 Psyche. We've had osiris-rex that just had the sample return. Tell me a little bit about those missions and how, as a planetary scientist, how do they excite you? What do you get out of missions like those?
So the Psyche mission to 16 Psyche is very cool because it's going to an entirely different type of planetary body that we've never been to before. It's going to a metal world. So Psyche is this asteroid. It's kind of like this potato-shaped asteroid. It's about 170 miles across, and it's way more metal rich than anything else. So on the surface, we actually see a lot of iron from telescopic observations here. And so the question is, what's a metal world like, right? We know rock worlds, we know water worlds, we know gas worlds, but what's a metal world like? And so it'll be really interesting to see, what does a volcano look like on this thing? What does an impact crater look like on a thing? And the reason we want to understand it is actually because this metal world is basically a giant ball of iron, is probably very similar to the iron at the center of the Earth. So we believe 16 Psyche is the leftover of some collision that hit an asteroid way back when and left just the iron core exposed. So going to 16 Psyche is kind of like being able to journey to the center of the Earth and going and studying our core.
Yeah.
So we're
without
really
all that
excited
pressure
to
and heat.
see. Yeah, exactly.
Yeah.
So it's like an easy way to go investigate the core of a planet. So that's very exciting.
Cool. Is there anything else that maybe doesn't hit the top of the list, but Psyche could be?
So yes, and right. So
Yeah.
we know it's metal rich, right?
Right.
And so how do you make that? Is it possible that something formed just out of the metals in an area? It's very unlikely, but you can never kind of rule it out, right?
Yeah.
But we think, in terms of the planets, Psyche might be quite similar to Mercury in a way. So the planet Mercury is also very small, and it has a large iron content, not as large as Psyche, but it does have a large iron content, and we don't fully understand how Mercury lost its rocky part, its outer mantle bit, but it might have been from a glancing collision that kind of tore off all the mantle, or it might have been from some sort of weird photoevaporation process that happened.
Yeah.
But Psyche might have these other weird mechanisms. So hopefully going there and taking detailed measurements from a variety of instruments will help to kind of unravel that question.
Absolutely. What about asteroid Bennu with osiris-rex?
So the amazing thing about the osiris-rex mission is that went there, booped an asteroid, picked up some stuff, and then brought it back to Earth. So we actually now have samples on the surface of the Earth of this asteroid.
Yeah.
That's really going to allow us. So the amazing thing about having samples on Earth is that we can do a lot more experiments, more detailed, careful experiments in labs here on Earth than we can put on a spacecraft that goes out there.
Yeah.
So people are going to really be studying these samples to understand fundamental questions about the building blocks of planets, right? Because all these asteroids, they're essentially leftovers from the building blocks when planets were forming. There used to be a bunch more small stuff. All that small stuff eventually kind of conglomerated together to make bigger stuff. And these asteroids are things that never made it in, right? So if you really want to understand the ingredients, right? Like it's like if you built a cake, right? If you baked a cake, right? And you wanted to know what was in the cake, it'd be helpful if you had the ingredients right beside you. And that would help you understand the process of baking the cake. And so similarly, when we analyze these samples, we're analyzing the ingredients that baked planets.
I love that. It's really crazy to me how much with missions like this, when we actually get to see it, or like the DART mission, for instance, where we impacted that dual asteroid system. I mean, not only were we able to look at, how did it deflect, we saw so much more debris than I know in the simulations it was more debris than that, but it seemed like it was a shower of debris. Are there certain things that you're excited about learning about? And I guess this is kind of a strange question, like, what don't you know that you're excited about? But are there like things that you have hope for that you're going to find on some of these new missions, whether it's, I mean, Juno's been doing amazing stuff. Are there any future missions you're excited about? I know there's a loaded question, but it's very exciting.
Yeah, it's loaded, but it's very easy to answer. So when I started my work as a PhD student, as I mentioned to you, I was doing magnetic fields of Uranus and Neptune. The Voyager 2 mission is the only mission that's gone out to our ice giant planets, Uranus and Neptune. That was in the 80s.
Right.
NASA has released its next decadal survey, which kind of talks about what its priorities are going to be for the next 10 years. And a mission to Uranus is on that list.
Yeah.
And like, that just makes me so happy because it's probably going to be in the end, like 50-ish years since our last visit. But that time frame is actually kind of good because you can actually do a lot of kind of comparative planetary science in that time frame. You can ask, how much did the magnetic field change in 50 years, right? As opposed to kind of seeing it on a daily basis. Of course, I'd love to have like constant monitoring of every planet, but
Uranus
we get what we can. Exactly. So I'm excited for this future Uranus mission, and I hope that everything goes on with it. The other interesting thing about it, and this is just generally how planetary science works, is that, I'm probably going to be retired by the time this mission actually goes. So my role, I feel right now in this mission, is almost to be a steward, to bring, to train new planetary scientists and prepare them for when this mission goes, right? I'm kind of that link between that old mission trained me and now I'm going to train the next mission. So it's a really interesting role that you end up getting in planetary science. You work on these projects that you might not live to see the actual result of them actually happen.
I love that. And to get a little philosophical for a second, I see this even if you're in a job and you've got some new employees, it's any field, and you're trying to train them and stuff like that. It really is like passing a flame. Like a flame is an amazing thing that it doesn't destroy the flame to make another flame, and it just you can keep doing that. So in essence, you're kind of lighting these candles so that when we get to that point, we're ready. There's more people. You couldn't do all the science anyways. So even if you wanted to, yeah,
exactly.
Oh, I love that. So tell me a little bit about the book. What was the process of this? I'm always interested, especially in a scientific book. What were some things you had in mind? Was there a person on the other side of it? Was there a mission for you? How did you go about it?
Yeah, I think so. First of all, I wanted to get across the fact that you typically hear people talk about how they stare up at the sky and at space, and they're wondrous about it, right? They're amazed by what they see. And I was hoping to kind of get the same sort of reaction if you were to stare down at your feet and just ask the question, what are all those amazing things happening 1,000 miles, 2,000 miles below my feet? And so that was sort of my my inspiration for writing the book.
Yeah.
And working with a great science writer, John Wentz, we talked about we talked about, right, what are the things that people would find particularly compelling? And I know for me as a scientist, the things that I find compelling. And so it was really great to be able to talk to someone and be like, is this compelling? Like, is this compelling to
I really love this.
This is where but what I discovered from that process is most of the stuff that I think is cool, the regular public thinks is cool too. So that's good.
That's good. That's good.
Yeah. But I really, yeah, it's always good. One thing I wanted that I never appreciated and I found cool when learning about this stuff, it was something I wanted to get across in the book, is that, on the surface of the earth, we're used to materials behaving in a certain way. Like if you think about water, you understand water, right? It's liquid, maybe it's frozen, maybe it's water vapor, but you think you understand water. But then you ask the question, well, now put it under 1 million bars of atmosphere pressure and thousands of degrees in temperature, and tell me what water's like. And you discover is that materials completely change the way they behave when they're under really high pressure and temperature. And you get all sorts of neat phenomena. So in my book, I talk about, for example, the fact that there are probably diamond icebergs floating on a diamond ocean near the center of Neptune and Uranus, right? Not something we have here on Earth.
No.
That in Saturn and Jupiter, there's something called helium rain. There's iron snow in Mercury, right? So there's all these interesting phenomena that occur because materials are just different when the pressure and temperature are really high.
I love that. There's so much that that it seems like we can learn, even just like I love your perspective. I think Neil deGrasse Tyson is definitely someone who's written, science books that have gotten people to look up. So I love that you're doing the opposite in a very I want to say similar style, that it's very easy to connect. Is there anything about, say, meteorites that happen to hit the planet or that we can recover? Is there anything like, what do you look for in that? Or do you guys get, as planetary scientists, a lot of people saying, hey, here's my meteorite, check this out? Like, we found this in our backyard. Really?
Yes, this is amazing. So this was probably 3 or 4 years ago. We were all kind of sitting around in my department having coffee, and this father and son walked in, and they had just been on a walk in the Baltimore area. And they came in and they're like, we found this strange iron-rich rock. We're wondering if it's a meteorite. Could you check for us? And unfortunately, we had to tell them that because of where they found it, it was likely from like an ore processing that happened in a while. So it wasn't a meteorite, but you do get that. And we also, interestingly, get the other side of things too, where, we have some really cool rock collections that were collected by previous professors over years and years. And now they're just kind of left, but they're not well categorized or cataloged. So every now and then you just decide to go, I'm going to go try and figure out where all the rocks are. And you go and you find a really cool rock, and you might find a meteorite. You're like, oh, look, this is a meteorite, right? So
That's pretty cool.
It's interesting to see what people have kind of hidden away in places that they didn't realize.
Yeah, it seems like there's so much. You were describing some place in the book, and forgive me for not knowing this. But there's like a specific place where there's all of these different types of rocks that I think geologists go to, if I'm not mistaken. You mentioned it. I think it was in the preface.
In the preface, let me think. In the preface, I mentioned I mentioned Sudbury, Ontario, which was the town I grew up in.
Oh, okay. So
So
that's
that was the impact crater.
gotcha. So
But
tell me more
actually,
about that. Go ahead. Sorry.
yeah. So I think this is what you're referring to. So, not only did that make Sudbury a place that had lots of natural resources that people would mine, but it also ended up making the surface quite similar to what we expect on the moon. So, for example, Apollo astronauts would come to Sudbury to train, to understand what kind of rocks to look for that would be interesting when they got to the moon and collected rocks.
Yeah.
So a lot of the rocks in Sudbury, because the impact smashed them and caused like sort of huge shock effects in them, they have very specific features on them that tell you they were affected by the shock. And we were interested in finding similar rocks on the moon. So Sudbury was kind of a hotbed for astronaut training
Cool.
in the 60s because of this fact. So yeah.
Are there any other impact places like that on Earth that you visited or that you know of?
Yeah, so Sudbury's when I was younger, we said the second largest, but now we have to say the third largest impact crater on the planet. It got beat out by the Chicxulub impact crater, which is in the Yucatan Peninsula and was related to what destroyed the dinosaurs way back when. So that one's a little bit bigger of an impact crater, and the largest impact crater is in South Africa. Sudbury's pretty big, but there are impact craters all over the place. You might have seen, or people might have seen, the Arizona crater. That's a really nice visual if you're ever flying across the country. You can actually, your plane might go over that. But there are other interesting impact places. So I live in Baltimore, and the Chesapeake Bay was actually formed because of the meteor impact here long ago. So they're all over the place. The planet was covered in meteor impacts over time.
Yeah, and it's crazy. Like I think one of the things that's I've seen online a lot is people talking about our moon and the impacts that it has on it, and how people are confused why the side that faces us have impact craters like all the time when you would think it's the back. And I think it's a good segue for kind of the scale, I think, of what you're dealing with. And you talked about obviously how different materials react in different pressures and temperatures that are just extreme. Let's talk a little bit about gravity and mass and time for the planetary scientist. How do you use those? How do those play in your kind of day-to-day, and what do they mean for you that it might not mean for the average everyday person?
That's a great question. I'll start with gravity. Let's start with gravity. So here on Earth, we think of gravity as being this fixed number, about 9.8 meters per second squared. If you're doing your high school physics classes, that's the number you plug into your physics problems to get it, right? But the reality is that gravity actually changes all over the Earth. So as you are walking around, you are feeling a different gravitational acceleration. It's a very tiny change, so we don't notice it, but we can measure it. And the amazing thing about being able to measure it is that the gravity you're sensing at any one location is actually due to the mass that's right below you. So when you see little differences in gravity as you're walking along, you're learning about how much mass is below you, and that gets you to what your composition of material is below you. So we can actually image the interior of the Earth using gravity. The same is true for other planets. The Grail mission to the moon did the same thing at the moon. The wonderful thing about the moon is that you can get really close to the surface and fly around, and so the annoying thing, let me put it this way, the annoying thing about Earth is that you have all these, first of all, you have all these surface feet, you have vegetation and land and things that we've developed that kind of hide a bunch of the surface features, whereas on the moon, that's all laid bare. You can see everything. So that allows us to kind of correlate the gravity signals we see with the actual topography and the shape of the surface that we see on the moon.
Right.
And from that, you can learn a lot too.
Crazy. Yeah. So let's talk about mass and time. So obviously, well, you talked about mass. I guess gravity and mass are pretty.
Yeah, you're right. They're
interlinked.
related.
Time.
You want me to talk about time? So time's an interesting one because in many ways, the geologist thinks in much longer time scales than us human scales, right? It's so funny when I'm teaching something or talking about something and I say, so for example, the formation of the Earth, right? And I talk about how fast you went from like a tiny pebble to something about the size of Earth today. And you always say, and it was really fast, like 1 million years. And you're like, okay, maybe that's not fast to you, but it's fast on a geological time frame, right?
Yeah.
So that's one thing I like to think of with time is that we think in really long time scales, but some processes you wouldn't expect actually are really short. So for example, the way our moon formed was that some sort of Mars-sized body, usually called Theia, smashed into Earth on a glancing impact, and that flung out a bunch of debris from both Theia and Earth, the proto-Earth at the time, and created a disk around the Earth. And you could ask the question, how long did it take that disk to become the moon?
Yeah.
And every time I say this answer to someone, they're like, and the answer is 40 years.
Whoa.
Yeah. So you could be like a kid. If life existed back then, you could be like a kid, and then you're in your like 50s and you could tell your grandkids, when I was young, there was no moon, right? And so
it was just a disk.
It was just a disk. Right? So that kind of process actually does happen on a human lifetime scale.
Wow. So break that down for me. What kind of things are happening? Is it like extreme cooling and I guess are they all impacting each other and just solidifying?
So basically, you've got this disk of particles and gas surrounding the Earth, and they're subject to the same sort of gravitational attraction that any two masses are. And just because of the distribution in the disk and the width and stuff, it doesn't take that long for them to all come together and form the moon.
Wild. That is, yeah. That is shocking. 40 years is crazy. That must have been, man. If you could be on the planet to watch that, that would have been crazy.
That would have been really cool.
Yeah. And is it true that it's moons come in as a disk and then leave as a disk? Is that true?
Ooh.
Do they start to break down?
So that's interesting. So it depends. So our moon is kind of neat because the way that the Earth and the moon interact, the moon is steadily moving away from us.
Right.
So it's just going to keep doing that for like 50 billion years, right?
Yeah.
But then you go to some of the moons surrounding Mars, for example, or moons in the outer solar system surrounding the giant planets, and some of them are actually moving inwards. And if you move inwards too much, then you fall into what's called like the Roche limit of the planet, which is where you'll be tidally broken up. You'll essentially experience so many stresses from the gravity of the planet that you'll be flung apart, broken apart, and then into a disk. So for some moons, that might end up being the conclusion of the moon. And in fact, one hypothesis for Saturn's rings is that they formed from a moon that essentially got broken up.
Wow. Now, Saturn and Jupiter are really interesting because they have so many moons. Do we see any interesting patterns with their layout? Are there different types, like some going away, some coming in? How does it work there?
Yeah, so basically everything, right? There's all sorts of stuff. The neat thing about moons is there's kind of two ways that you can get a moon as a planet. You could have a disk that surrounds the planet, just like the protoplanetary disk surrounded the sun. And in that disk, you could have the same type of processes that created the planets happen. So for example, at Jupiter, the 4 Galilean satellites, Io, Europa, Ganymede, and Callisto, they're pretty big, they're spherical, and they probably formed from a disk that surrounded Jupiter. And they're all kind of coplanar and they all orbit the planet in the same way. But then you also have these moons that are on weird orbital angles, and some of them are orbiting backwards compared to the rest of the planet and everything. And those are probably captured objects. So those are probably asteroids or comets that used to live very happily out in the outer solar system, doing their own thing, but then got kind of gravitationally attracted to and kind of stuck to Jupiter, Saturn, Uranus, and Neptune.
Yeah.
And so you get these moons that can behave much more wildly than the other moons because they were just kind of passing by and they got kind of tractor beamed into the
Sucked
planet
in,
and
yeah.
stuck there. Yeah.
Oh, cool. Okay, two-part question for you. Number one, is Pluto a planet? And number two, what about New Horizons and what we've learned from there? What does it tell you, especially with how young the surface seems to be?
Okay, so here's my answer for is Pluto a planet? The answer is no, but it's still way cooler that it's not a planet.
I'm with you.
Okay, good.
Yeah.
So basically,
unpopular, but I'm with you.
yeah, it got to create its own class of planetary objects, right? Because of Pluto, we have this new thing called dwarf planets, and so it's like it's a leader. It's you know, started
it's the king of the Kuiper Belt.
Exactly. So I say Pluto is not a planet, but that doesn't mean it's not cool.
Exactly.
In terms of the mission, New Horizons, to me, like, it was just fascinating to see the images of both Pluto and Charon as New Horizons flew by. And you look at that region of of Pluto, there's a region of Pluto that's kind of bright and shiny, and it's shaped like a heart, which is very cute.
Great.
And it's got all sorts of processes happening in it. We see ice flow in that region. We see signs of kind of like the stuff shifting around and moving around, stuff like rolling over, all these things that indicate that there's probably a heat source a little bit deeper inside there, and it's causing all sorts of tectonic activity. So the amazing thing to me is that Pluto's not dead, right?
Yeah.
In some ways, it's not this cold, barren place where nothing's happening. No, there's like a healthy, invigorated interior to that planet, causing all sorts of features on the surface.
Yeah, and it's such a, I mean, what a beautiful moment to just capture on that flyby. I mean, flyby missions, we don't get many of them, especially one with the kind of detailed science and visual data that New Horizons had. But it's amazing to think that just in one flyby, all the books got rewritten like overnight. It's crazy.
Yeah, to me, that's the amazing thing about planetary science is every mission you send to a planet, you're like, okay, we got to rewrite the textbooks because we're going to discover entirely new things, and because we can build on our previous knowledge. And it's amazing to see how fast things change when you get new data from planets.
Absolutely. Do you I see this, so I work as an engineer. I'm in additive technology right now. One thing that I have found myself trying to help the scientific community grow, the idea of scientists and engineers speaking in what's the word I'm looking for? Solidarities, like this can't be done or this is what it is. As a planetary scientist, do you see that there is some of that kind of like, well, we know the answer, there's no, almost like there's a, I don't want to learn something new, so let's not go explore that. I don't think it's anything that anyone's doing necessarily on purpose, but I think it's something, as people in science, I think it's something to bring up because I think it's only doing us a disservice. So I'd love to know your take on that and how scientific just saying I don't know is.
Yeah, great question. I think it's like this two-edged sword, right? In many ways, we're scientists, and the key thing about science is that new data results in new understandings, and so we have to follow the data. We can't pretend we didn't see that data and just believe the old thing, right? It's just built into it. The fear sometimes of saying I don't know or we don't know is that people then interpret that to mean, oh, scientists don't know anything, so it can't, right? And so there's a difference between how certain we are of things versus how probable things are. And I think scientists like to speak, if they're kind of speaking to other scientists, they like to use as specific as possible kind of an explanation for things. But when that translates to the general public, it doesn't always translate, right?
Yeah.
For example, the IPCC climate change reports that come out, they use very specific language. Like when they say most likely or possibly, like those have very specific scientific meanings to them that they lay out in the document because they wanted to avoid this issue. But I think it's important that we tell people when we don't know things, because that's why we still need more scientists to do more science, right? Like I love saying, none of us know how that works. Imagine what we're going to find out when we go there, right? So I think that's definitely important. You also see, of course, you're going to see people who have their, let's say, pet theory or pet idea that they're refuse to hang up, right? Refuse to give up on. Sometimes it's because it makes a lot of sense, right? But you need to kind of have enough data to show, yeah, that made sense, but it doesn't really work because it can't explain X, Y, and Z.
Yeah.
And sometimes it's hard. I think the key thing to remember here is scientists are humans.
Yes.
And humans very much have their own kind of biases and beliefs and so forth. And so you have to kind of always try and keep yourself grounded and understand that, you know, your ego is not embedded in that thing you discovered or that theory you have, right? The important thing about being a scientist is to be able to change and to follow the reasoning and the data.
I love that. And I couldn't agree more. You know, in the world that we live in today, I find myself looking back to Einstein and his time. Just the tumultuousness of the world wars, how his friend Fritz Haber went from this amazing scientist to, you know, changing world hunger to obviously going the exact opposite way with it. And then he goes from that to fighting the scientific community, trying to show that special relativity, general relativity, is this new thing. And then even when getting that evidence from that eclipse, still has to fight with the scientific community to get this. But today is seen as this groundbreaking thing that now someone else is trying to, you know, jump the next thing. For me, we talk about this thing called the space conundrum, where we're in this period of time similar to that, but more to, I would say, the Cold War, where we're in this space race right now. Access to space is exploding. We're able to do so much more in space than we ever were before, but at the same time, the social problems and civil rights and all these other things and chaos is coming up at the same time. I don't have an answer for why that's the case, but it does seem to be cyclical in some kind of nature. Do you see the same thing right now as a planetary scientist? Are you seeing this boom of space interest and an economy, and where do you think we could best utilize that at the moment?
Great question. I think one of the things that's really driving stuff right now, and this has changed even in the last 20 years, I would say, so even when I was a grad student, is that it used to be that if you were someone like me, which means that I was interested in science, I loved the idea of exploring new things, but I also wanted some independence and freedom in choosing what I wanted to study and what I wanted to learn. The only place that you could do that really was higher education, academia. Nowadays, that's not the case. Nowadays, if you have the right toolkit, right, if you have skills in data analysis, skills in machine learning, skills in experimental sciences, lab-based work, a lot of nonprofit agencies, private industry, government agencies are doing this kind of work, and they're basically giving people that same amount of freedom as you might have in academia. So there's a lot more opportunities out there right now to do scientific work without being kind of in a very specific environment, right? So maybe the academic environment's not for you. That's okay. You can go work at NASA, or you can go work for a private space company, right? So there's all sorts of different places where you can do this work. So I think that the more times you bring in a diversity of perspectives and a diversity of goals in doing any sort of research, you get a kind of a growth. You get growth in the field. And I think that's why we're seeing a lot of growth in science in general, but planetary science also, is that there's just more different groups of people working on the problems.
Yeah. And that's a beautiful message. I mean, part of this People of Science segment, part of the reason why it even exists is because, I would field so many questions from people about, hey, I used to work in STEM, or hey, I want to work in STEM. How do I get into this? And so being able to speak with you and so many other different people and all their different backgrounds, I think is super important. I think to close out here, your non-traditional path to science, I think is really important. That it wasn't necessarily like the thing that as a child you were like, I'm gonna do this. It's something that came later is great. And you talked about like almost skill stacking, which we've talked before. Just putting together some skills that's going to allow you to do the thing that you want to do, instead of necessarily, like you're saying, the traditional path of go to school to learn all your skills and then there's a job for you on the other side. Is there any other kind of advice you would have for anyone who's in that position that we haven't touched on yet?
Yeah, I think I'm going to give some advice that I wish someone had told me when I was younger. And honestly, even if they had told me, I probably wouldn't have followed it. But still, one thing that I think is really important is to not be afraid to fail at things. I think a lot of times we end up doing the things we're doing because we were kind of good at them. We had some success in them, so we may as well keep going in that. But I think in order to have real growth, you need to try things and fail at them and learn from that. And it doesn't necessarily mean that you can't do that, but maybe you'll learn something from that that'll help you in some other thing. You never know, right? So right. I really want people, the advice I would give kind of people who are thinking about going into science or in any field really is be willing to experiment, right? And try things and discover that, oh, you know what, that thing was not for me, but that's an important data point to have, right? So don't be afraid of failure, learn from failure, because you can learn the most from failure actually. But try things and you won't know what you like until you try it, basically.
Yeah, thank you. That was perfect. So folks, Dr. Sabine Stanley, thank you so much for being on. Please go check out her book, What's Hidden Inside Planets. Sorry, I couldn't read that backwards on my screen there. We'll have a link here in this episode if you want to go check it out. It's available from Hopkins Press. Dr. Sabine Stanley, thank you so much for being a guest here on the podcast.
Thanks so much. This was very fun.
Spread love and spread science, everybody. We'll see you on the next episode of Today in Space. See ya.